Okay, last time we studied that the total emitted power from a relativistically moving charge, moving and accelerated charge. So the formula we derived was 2 over 3 e square over c gamma to the 6th power beta dot square plus beta cross beta dot square. So that was the linear result. So in 1898, so this is a total power, and we said that when the charged particle moving non-relativistically, when beta goes to 0 and gamma goes to 1, that reduced the classical Larmor result. The total power is 2 over 3 e square over c. So this term drops, gamma goes to 1, and you can obtain the Larmor result or Larmor formula. So basically beta dot is the acceleration. If you know that the acceleration of the charged particle non-relativistically, you can find that the total power, and relativistically also you can find the particles emitted total power. So we studied two cases. One is the beta and beta dot parallel to each other in relativistic case. That was for the linear acceleration, and the other was for the circular, and in that case beta is perpendicular to the beta dot. So today we will study that the radiation pattern of the relativistically accelerated charges for two cases, for linear and circularly moving charges. And then we will study that the intensity spectrum is a function of the frequency or energy of the emitted radiation. So let us study that the angular distribution of the radiation from the accelerated charges. So what we have at hand, Poynting vector, that is c over 4 pi in Gaussian units E cross B, and B is n cross E. We don't have a 1 over 2 factor because these are not the oscillating fields, they are the radiating fields. So if you put things here, you can obtain c over 4 pi magnitude square of field along n. So you can use that double cross product rule very easily. E dot E along n, E dot B is equal to 0. So E dot E along n, E square n, and minus E dot n is equal to 0. Therefore, the surviving term will be in that form. And the field of the accelerating charge in general is the following. So we derived this last week. N cross n minus beta dot, or beta cross acceleration divided by 1 minus beta dot n cube over r evaluated at retarded time. So n cross n minus beta cross beta dot. So this is the field of the accelerating charged particle relativistically. So if you want to write that total emitted energy per area, so this is a unit of what? Energy per second per area. So if you are interested in, let's say, energy emitted per area, all you have to do S dot n, all of them are evaluated at retarded time. This is the intensity, it's a scalar quantity and is the point of interest. So the surface of the unit vector, surface of the the vector perpendicular to surface at which the waves are propagating. So suppose that this is the S and this is the surface you are interested in. So S dot n is the intensity passing from the any surface, and if you integrate this through the time from one time to another, let's say T1 to T2, you can calculate that let's say energy per area, let's say E energy per area. So these are the times we already observed the radiation. Radiation is emitted at retarded time and we observe with the actual R time. So what we are going to do, we know one thing, T1 is nothing but T1 prime plus R over C. So this is the source time at which the time is corresponding to the source time, let's say, at which the radiation emitted, and the radiation is propagated in vacuum with the speed of light, and R is nothing but x minus x prime magnitude. So basically we have the source, so the source is changing its path. We are observing the radiation somewhere here. So when the radiation is emitted here at T prime, so it propagates here at R over C, x minus x prime magnitude over C. When we observe the radiation here, the charged particle is in the different point, different location. So here the times are the times we are observing the radiation, and similarly T2 could be written as T2 prime plus R over C. So T primes represents the at which the radiation emitted, and the T's are represents the we observe the radiation. So if you want to calculate the total energy per area in a time interval between T1 and T2, you can write this as a T1 prime plus R over C. Let's say T1 prime here, and some later here, that is the T2 prime. The radiation emitted and propagates here, but the charge is not here, the charge is somewhere else. So what I am trying to do, I am trying to write that the radiation pattern, angular distribution of the radiation with respect to the charge, moving charge. So what I am going to do, I will change the integration limits. I will change the integration limits. So what I am going to do, S dot n at retarded time, so dt, and multiply by dt prime, divide by dt prime. So then the integration is taken with respect to charge location, the coordinate, time coordinate of the charge. So therefore this have to be evaluated from T1 prime to T2 prime. not from T1 to T2. It should be evaluated T1 prime to the T2 prime. T1 prime and T2 prime are the times seen, time coordinates seen with the charge. Then I can call this whole quantity in the integral as a 1 over r square, the power emitted at t prime over Solute angle. Okay, so basically this is nothing but s dot n observed at t prime. So basically this is equal to s dot n dt over dt prime, and if I multiply both sides r square, I will obtain that the power emitted per unit Solute angle with respect to the moving charge, if dt over dt prime is 1, then that represents the non-relativistically moving charge. That represents to the power emitted per Solute angle non-relativistically moving charge. So at this point I have to calculate what is dt over dt prime. I know that what is dt over dt prime because t is nothing but t prime plus r over c. So I can calculate the dt over dt prime very easily. So t in t prime plus r over c. So as we said that here, when the charge is moved in its trajectory, we call this is a x prime, this is t, this location is t prime, and this location is the coordinates of x and t. So let's say this is x and t, and that is x prime and t prime. So when the radiation emitted, it takes some time to propagate to observer, and at that time the charge changes its locations. So if I take the time derivative of this, I will obtain dt prime plus dr over c. So take the dt prime parenthesis, that will be dt prime 1 plus dr over dt prime 1 over c. So this will be that. So what is dr over dt prime? So let us draw the coordinates again. So let's say that the charge at x prime location moves some velocity v, and x is our point of interest, and x minus x prime is this vector, and you can write the magnitude as a r. So what happens here, when the charge is moving here, x minus x prime is changes. So dr over dt prime is related to velocity of the this length, and this length is decreasing when angle is less than 90 degrees, and increasing when the angle is greater than 90 degrees. So you can express this factor in the following form. So let me write here, or here again, let me write one more line. This is equal to dt prime 1 minus beta dot n. Beta is v over c, n is the n unit vector, and unit vector is the direction of n hat. So basically v dot n is negative when the angle is less than 90 degrees. That means that r is decreasing in time, and beta dot n is what? minus and one more minus positive when angle is greater than pi over 2. So that represents the change of the length of the r, this beta dot n. So basically what we are obtaining now, let us write again, power emitted per Solute angle at the frame of the charge will be r square s dot n dt over dt prime. Dt over dt prime is nothing but 1 minus beta dot n. Now let us calculate this. What is s dot n? S is related with e square. S dot n will be what? N dot n will be 1. So that is related c times c over 4 times the square of the accelerating field of the accelerating charge particle. So the result will be the following: c over 4 pi from the definition of the S, square of the electric field brings the following things: e square over there divided c square, and the square of this term, whole term, square of whole term, and cross n minus beta cross beta dot divided by, let us take the square of this, divided by the square of that term, that brings is 1 minus beta dot n to the 6th power, and we have r square here, but r square there, that will be cancelled out, r square here and r square will be cancelled out, and we have a factor when we carry the coordinates with the reference frame of the charge, that is 1 minus beta dot n. So basically one factor of decrease of the 1 minus beta dot n. So the angular distribution of the radiation with respect to the Solute angle will be the following. So this will be decreased one factor, and we will have what? E square, one of the c's will be cancelled, 4 pi over c n cross n minus beta cross beta dot square 1 minus beta dot to the 5th power. So this is the form of the angular distribution of the radiation as a function of Solute angle. But what is this? So it's some bunch of formulas. So let us try to interpret what is this. One thing you can do, you can look at the case when beta and beta dot parallel to each other, linear acceleration, if the charge is linearly accelerating. So let us look at what is going on first for linear acceleration. When beta and beta dot parallel to each other, what kind of radiation pattern we have? So basically beta and beta dot parallel to each other, beta cross beta dot will be 0, the other terms will be survive, and that is nothing but the following. So when beta parallel to the beta dot, we will obtain the distribution of the radiation is a function of angle, Solute angle, E square over 4 pi c. This beta cross beta dot term will be 0, then that will be what? N cross N minus N so these terms will be dropped. So which term will be survive? Oh, N cross beta dot will be survive. N cross beta dot term will be survive. That should be divided by 1 minus beta dot to the 5th power. Yes. So basically, let us look at here. Beta and beta dot parallel to each other, and we are looking somewhere else, and that is the angle between beta and beta dot. So n cross beta dot is sine theta, and the n cross, if it doesn't change the sine theta, there will be pi over 2, because n cross beta dot is orthogonal to the n. So you will obtain the following: E square over 4 pi over c, beta dot square sine square theta divided by 1 minus beta dot n. Beta dot n is beta cosine theta to the 5th power. Again, we are seeing some functional form depending on theta, okay. And one thing we can do at this point, look at what is going on in the low speeds. So when beta goes to 0, in the non-relativistic case, and beta dot, of course, is not 0, and this term will drop to the 0, and you will obtain the radiation pattern in non-relativistic case is E square over 4 pi over c. Beta dot is nothing but acceleration over c, and square, that makes to c cubed, and the square of the acceleration sine square theta. So this formula is known. So this is the dipole pattern. We know this pattern. So when the acceleration is non-relativistic, the distribution of the radiation is a pure dipolar form. So this is the angle theta, and the radiation is maximum at pi over 2 and drops in the forward direction. And this is the case, we derive this. So this is agreed with what we have done, dp over the Solute angle, power emitted per Solute angle, for the case of the non-relativistic case. So if you look at the lecture notes, this is the identical form. So basically this formula is working well in non-relativistic case. So if you look at the lecture notes, when we derive the Larmor formula, we first obtained that the power emitted per Solute angle, then we integrated through the Solute angle, and we find that the Larmor formula, which is valid in the non-relativistic case, and this formula is exactly the same. So the bottom line, if the acceleration and the velocity parallel to each other, and if this is non-relativistic, we have the dipole radiation. And what happens if the acceleration is relativistic? so if the charge is moving relativistically, not the acceleration, the charge is moving relativistically. So this situation is the following. So if beta high, so it's if beta high, so close to the 1, less than 1, close to less than 1, you can find that the angular distribution, so basically the structure you have to know, all you can find that the maximum value of the radiation depending on the angle, so you attempt to derive, but there is no need to attempt. So the final form is important. 1/3 beta 1 plus 15 beta square minus 1. So this is just a formulation. The important thing, this is, if you do carefully, this is proportional to 1/2 gamma. So this is important. If gamma is 10 on 100, that means that the angle is very small. So what does it tell us? If the charged particle is in linear acceleration and relativistically moving, the radiation pattern is something like this in forward direction. And this angle is theta maximum is 1/2 gamma. So this is the form of the radiation in the relativistic case and for the linear acceleration, and this is the pure dipole pattern in the non-relativistic case. So if the charge is accelerating and moving relativistically, all the beam pattern forwardly collapse and making an angle around 1/2 gamma. Is gamma maybe 10, 100, 1000, okay, for a highly relativistically accelerated charged particle. And if you look at the beam, so the power emitted per Solute angle, so if you plot in terms of gamma times theta, so gamma times theta, this form is the following. In just ahead in the forward direction, the radiation is 0, but then it amplifies and everything is in the region of gamma beta is 1. Gamma beta is 1. So, and it is the symmetric, so this is something like this. So power emitted per Solute angle squeezed the region gamma beta is equal to 1 and minus 1. So all the radiation is squeezed here. Very small angle, but just ahead that is 0. Okay, so one thing you have to keep in your mind, the radiation pattern of the relativistically accelerated charge for the linear acceleration. So the next thing I am going to do, look at the, there's one thing I have to mention. There is one, so is this formula is consistent with the linear results. So we can look at this, What you are going to do, you should integrate this through the all Solute angles. So you have the power emitted per Solute angle written with respect to the source coordinate, source time coordinate. If you integrate this through the all Solute angles, you will find that the total emitted power, and if you do this algebra, you will find that the result 2/3 E square over C cube times the acceleration square gamma to the 6. Actually, if you compare with the linear result, they are identical, because in that case beta cross beta dot is 0, and this term is the total power emitted for an accelerated charge, linearly accelerated charge, that is 2 over 3 e square over c gamma to the 6 beta dot square, and this is the same 2 over 3 e square and beta dot square over c gamma to the 6. Okay, so basically this is working well with the linear results if you integrate through the all Solute angles. Now, as you guess, what I am going to do next, I will concentrate to the circular motion that is mostly using the cyclotron radiation, and let us look at the radiation pattern if the relativistically circulating charge. So basically, if beta and beta dot parallel to each other, I have shown you that the radiation pattern is something like this. That is 1 over 2 gamma is the angular distribution, and the case for the circular motion is the following. So let's say this is x, y, and z, and let us have the circularly moving or curvature of the radius at any instant. Let's say that the charge is moving here in that path. So at here, let's say that the beta at that instant, beta is along the z direction, and the beta dot is pointed to the curvature of radius beta dot in this direction, and we are looking at the radiation at any point n. So basically n hat is the following. So these are the theta phi is the angular distribution, angular spherical coordinates. So n hat is equal to cosine theta along to k hat, sine theta sine phi along j, sine theta cosine phi along I. Okay, so you can, this is the theta, this is the phi. Okay, this is the unit vector. What we are trying to calculate, we are trying to calculate the power emitted per Solute angle, this kind of motion. So the trajectory is circular at any instant, beta is along the z, beta dot along the x hat. So what we are going to do, so I will show you how we are going to calculate the power emitted per Solute angle, and then I will talk about just the results. So this is the general formula here. Beta and beta cross are orthogonal to each other. You can express this as a rule of the double cross product. So that is nothing but the following: n dot beta dot along n minus beta minus n dot n minus b along beta dot, n dot beta dot along n minus beta minus n dot n minus beta along beta dot. So let me write this, you can see better. So in that formulation, what I have to calculate, n cross n minus beta cross beta dot, this is equal to n dot beta dot along n minus beta minus n dot n minus beta along beta dot. Then I have to take the square of this. But I will not do everything. I will show you what you are going to do. What is n dot beta dot? What is n dot beta dot? N is along ijk and beta dot is along only I direction. So n dot beta dot will be this term, sine theta cosine phi times beta dot. So for this piece you can write beta dot sine theta cosine phi because beta dot is along the I direction, and you have n minus beta. And how about this one? N dot n is 1. N dot beta, what is n dot beta? Beta along the z direction, n dot beta is nothing but cosine theta. And the direction is beta head. Okay, this is the piece, first piece. Then, so this is a piece for the power emitted per Solute angle. So look at here. So I am doing this part. So what I need, I have to take the square of this. The next, I have to take the square of this, n cross n minus beta cross beta dot, and take the square of this. So what will be the square? The square terms will be the following: beta dot square sine square theta cosine square phi, and the square of this first term, that is nothing but n dot n is 1 minus 2 n dot beta plus beta square. So square of the first term, have the n dot beta. N dot beta, what is n dot beta? N dot beta is cosine theta. And then you have the square of the second term. So let us say that the square of the second term, this is the second term, 1 minus cosine theta square beta dot square. This is the square of the second term. And then we have the 2 times of the scalar product of this, minus 2 beta dot sine theta cosine phi, sine theta cosine phi, and 1 minus cosine theta. So I am taking the 2 times of the scalar product of these two. I write the 2 beta dot sine theta cosine phi and 1 minus cosine theta. And if you look at the dot product of this, you have n dot beta dot and beta dot beta dot. So you will have 2 terms here, n dot beta dot and minus beta dot beta dot. This term will be 0, and n dot beta dot will be what? N dot beta dot. So this is the beta dot along the I direction. So n dot beta dot will be sine theta cosine phi. So this is the bunch of trivial algebra. So I show you that what you are going to do. So basically the situation is the following. If you collect the terms and plug in there, you will obtain that the radiation pattern per Solute angle. So let me say that, show that it is trivial. So you will find that the following result: E square over 4 pi c cube square of the acceleration divided by 1 minus beta cosine theta cube 1 minus sine square theta cosine square phi gamma square 1 minus beta cosine theta square. So it's a complicated function here. So what I'm going to do, I will just discuss what is going on geometrically. The situation is the following. So these are the trivial algebra parts. You can do the rest by yourself. The situation is the following. This formula tells the following. So basically, for that case, you have the acceleration in one direction and the velocity in other direction. This is a circular motion. If the charged particle is relativistically accelerating, the situation is the following. So if the charged particle is relativistically accelerating or non-relativistically accelerating first, this has the dipole form. So peaks along the acceleration direction. No, it's a dipole form. So peaks are perpendicular to the acceleration direction. But if the charge is accelerating in circular motion relativistically, the situation is the following. So this pattern, it will be the following. So, and this will be something like this. So basically this is the form of this. So if you investigate this pattern, you have that kind of shape. So basically this is around, this angular distribution is around 1 over gamma. So if the charge is, let's say, in the magnetic field, in the uniform magnetic field, if it is gyrating, it is illuminating to the motion of direction. So suppose that we have the uniform magnetic field and the charge is moving relativistically. So the radiation pattern is something like this. So here the radiation here, and when the charge here, the radiation pattern goes here, and here maybe something like this, like a light cone, light hole. So it's something like this. So these are the radiation patterns. So when the charge is moving, so think about this like a cone. So like a cone. Okay, so if the charge is accelerating relativistically, the angle of this roughly 1 over gamma again. So when the charge in the magnetic field is accelerating in circular motion, so illuminates the ahead of direction. Okay, just ahead of direction, and the width of this cone is roughly 1 over gamma factor. Okay, therefore in the cyclotron radiation, mostly we observe the cyclotron radiation, the case of the velocity and the acceleration perpendicular to each other, the emission pattern is like this. So it emits the forward direction purely. If it is non-relativistic, this is something like this, but if it is relativistic, it illuminates to the forward direction. And if you think about a cone, for example, cone, if it is velocity here and the acceleration here, the width of the cone is roughly 1 over gamma. So this complicated formula tells us this. So if you plot this, you will find that form, and you can take the limits at the high and gamma high, and you can find the angular width also by yourself. And if you integrate the power emitted per solute angle through the all solute angles, you will find that the total emitted power, and the total emitted power is 2/3 E square C cube V dot square gamma to the 4. If you compare with the linear result, if beta and beta dot perpendicular to each other, that is nothing but beta dot, and if you take the beta dot square, this will be 1 minus beta square. 1 minus beta square is 1 over gamma square, and that will be gamma to the 4, and that is consistent with the linear result. So you have to look at the lecture notes what we have done last time. So this is also consistent with the linear results. So the bottom line, what we learn here, if beta and beta dot parallel to the, in the case of linear acceleration, the radiation pattern is bent in the forward direction. But if you have the case of the circular motion, and if the charge is highly relativistically moving in circular motion, then you have this kind of radiation, cone-like of radiation, and the width of the angle is roughly 1 over gamma, the radiation band in the forward direction. So for the cyclotron emission, this is the case of the cyclotron emission. We will deal with the cyclotron emission next week, not in detail, qualitatively. Charge cyclotron means that the relativistically moving charge under the influence of the magnetic field. So if the charge is moving relativistically under the magnetic field, uniform magnetic field, let's say, so the emitted pattern will be in the forward direction. The emitted angle is proportional to 1 over gamma. So this formula is telling this. So you can work on this and show that the maximum value of the theta is related with the 1 over gamma. So basically, you know that the acceleration of the charged particle under the uniform magnetic field, that is very simple. So mv square over r is equal to the Lorentz force V cross B. And you can write this in relativistically. You can find that the acceleration, and you can find that the exact form of the emitted power per solute angle, or you can find that the total power from the cyclotron emission. So next thing, in the next hour, I will start to study that the distribution of the radiation as a function of intensity, as a function of the frequency or the energy. So basically you have the photons, number of photons given 4 different energy beams observationally. Then you need to know that the distribution of the intensity distribution of the photon is a function of the frequency. Because if you multiply with the Planck's constant, that will be the intensity versus what? Energy. Then you will have that the spectrum of the radiation. So next hour we will prepare ourselves to the spectrum of the radiation. Then next week we will do applications for this, for what? Cyclotron again, Cherenkov radiation, Bremsstrahlung, and the other concepts we will investigate the Thomson scattering and the radiation reaction force. So let us give a break, then we can continue.